got this rho thing here as well. But rho is a dummy variable, so it's just inside the integral. We don't really care about it. Hello, everybody, and welcome back to another episode of Edmund's Maths. Now, I'm very excited today because last time we derived these equations of motion for the motion of two particles which are in outer space and coming together through their own gravitational attraction. And today is going to be a lot of maths. We're going to be solving these equations of motion and finding x1 of t and x2 of t, i.e. the positions of the masses as functions of time. So, we need to start off by just staring at these equations and actually seeing what we can do with them, because these are a couple non-linear second-order ordinary differential equations, and in general, you can't solve those for your functions exactly. So we're going to need to be really quite clever to try and solve these. What I suggest you do is actually pause the video, have a go at solving these yourself with these initial conditions, and then we'll come and watch the rest of the video. Okay, so let's go ahead and try and integrate these. Now, first of all, if you were to stare at the equations long enough, then you see that there's this nasty x2 minus x1 term in here, and this is what's really screwing us over at the moment. So let's try and get x2 minus x1 on the left-hand side. So let's take equation 1, let's take equation 2 and subtract off equation 1. And this will give us x2 double dot minus x1 double dot is equal to this thing minus this thing. This will give us minus g over x2 minus x1 squared. Actually, all I'm doing is factoring this term out, because this term, this g over x2 minus x1 squared, is seen in both terms. And you'll just get, because you get minus 1, then you get m1 plus m2, because you'll actually see the minus sign in this term as well, because it's being subtracted, so it's perfectly valid to factor it out. Okay, this is still pretty horrible. However, you've got the x2 and x1 on the bottom there, and you've got something that looks like x2 minus x1 there. So let's do a substitution. I'm going to do this sort of blue pen, black pen style, black pen, red pen style, whatever you want to call it. So I'm going to use the substitution u equals x2 minus x1, where I've just kept in the function notation there just to make it explicitly clear that these are indeed functions of time. So we can do it u1 dot is equal to x2 dot minus x1 dot, and indeed u double dot equals x2 double dot minus x1 double dot. And we're now ready to just shove this in. So this thing is just this thing, which is this thing. So we get u double dot is equal to this junk on the top, which is just constant, so that just stays the same, divided by this thing here, which is this thing here, which is this thing here, squared. Okay, so we've got this for our equation now. It doesn't look any better, but let's just first of all make sure we've got our initial conditions in right. So we need to think about what is u of 0. Well, u of 0 is just u of t evaluated at t equals 0. So it's just going to be x2 of 0 minus x1 of 0. And x2 of 0 is a, and x1 of 0 is 0. So we get that equal to a minus 0, which is indeed just a. U dot of 0, well, that's just equal to x2 dot evaluated at t equals 0, which is just 0, minus x1 evaluated at t equals 0, which is 0. So that is just 0, because 0 minus 0 is equal to 0. Okay, so we've got something a bit nicer, right? We've now decoupled the equations. However, we've still got a non-linear second-order ordinary differential equation with two initial conditions, which still isn't very nice, to be quite honest. However, luckily, we've only got u on this side, and we haven't got any t's on this side, which means we can use a very nice trick, which is to to use the relationship that u double dot is equal to half d du of u dot squared. And this is something which I derived in a previous video. So please check the description and look at the way that this is derived, because I can't be bothered to do it here. So we can substitute that for that. So indeed, u dot is by this equation equal to this. So we get that this thing is equal to this thing. Okay, this still doesn't look very nice. In fact, it looks more horrible than that. But the great thing is that we've actually gotten rid of this second derivative. And we've actually got something which we can integrate with respect to u, and therefore actually at least integrate it once, which just brings us a little bit closer to the light at the end of the tunnel. Right, so okay, let's go ahead and integrate this bloody thing. So first of all, let's just put this. Let's just write d du u dot squared is equal to. Let's just move the 2 to the other side, so we get minus 2. G m1 plus m2. Let's just be careful, and that will be u to the minus 2. And that's a multiplication there. I always use dots as multiplication. And now, we can go ahead and just integrate both sides with respect to u. So I'm going to be integral du. All this stuff is constant, so this stuff can just go straight through the integral sign, and I can put a du here. Now, what are the limits? Well, we could just integrate this indefinitely, but it will actually prove easier to put the limit straight in later on. So I'm going to get used to that habit now. Essentially, what you'd normally do if you do the antiderivative and then put the initial conditions in, you get a constant, and you put the initial conditions in, you find the constant. However, you can also encode the initial conditions in the limits, which is probably something I'll do in a different video. So the lower limit can just be what everything is when t equals 0. So when t equals 0, u is equal to a. So that's going to be my lower limit. And here indeed u equals a. And then my top limit will just be when t is some general time. And when t is some general time, u will be just u of t. So this will be u of t here. Now, we can use the fundamental theorem of calculus, and we can say that this actually is just the integral of d u dot squared, where now we have u dot on the limit of integral, so of the limits of integration. So when u is equal to a, that's when t equals 0, and when t equals 0, u dot is equal to 0. So this lower limit, when t equals 0, is just going to be 0, and this top limit, when at general time t, then u dot will just be whatever it is at some random time t. So we can actually go ahead and perform the integration. Okay, so we now have this thing. Now this thing is just going to be, if you have, for example, integral of dx between x1 and x2, then that is just equal to x between x1 and x2. So you can just say that this thing is equal to u dot squared between the limits, which are 0 and u dot. I'm dropping the function notation because it should. I'll just make it very clear that we're actually trying to solve for this u of t, which is x1 of t minus x2 of t. That's the thing we're trying to get. Okay, so again, this is equal to this stuff here multiplied by this integral. Now, this is just a power integral, so you just add 1 to the power, that gives you u to the minus 1. You divide by the power, so you get divided by minus 1, which is the same as times 1 minus 1. So you get minus u to the minus 1 between the limits of a and u. So we can now just evaluate that very, very simply. So that's just u dot squared minus 0 squared, which is just 0, equals minus 2g m1 plus m2, and this thing here, which is minus 1 over u minus 1 over a, which is just plus 1 over a. And we can tidy this thing up, so we get the u dot squared is equal to minus, well, we can, oh, what I actually want to do is put the minus sign inside these brackets. So we get 2g m1 plus m2, 1 over u minus 1 over a. Now, this still doesn't look that good. Let's just make this thing look a bit better. So let's just combine these fractions. And when we combine the fractions, well, we get a minus u, bring that there, divided by a u. And so there. And this thing here, what is u dot? Well, u dot is just du by dt. So we can just write this as du by dt all squared is equal to this thing times that. So that's going to be 2g m1 plus m2 times by a minus u over a times u. Okay, so now after that beautiful journey through integration, we now have another differential equation. But fortunately, this one is also separable. But first of all, we need to get rid of this nasty squared thing. So, actually, let's just first of all do a little check, because if this is squared and du by dt is bloody well better be a real number, because this is a physical problem, so we expect this to actually be a, real values, real numbers. So, this thing's got to be greater than or equal to 0. Let's just check that's true, because we've got a minus here. So, this stuff's all positive. This is all positive. Remember, u is just actually the distance between the masses, because it's just x2 minus x1. That's what u is, just the distance between the masses. And so a minus u. Now, is a minus u, is that positive or negative? Well, remember the masses start a distance a apart, and then they're at a time t they're closer together, because the masses come closer together. So at a general time t, u of t, i.e. the distance between the masses, will actually be less than a. So therefore, if u is less than a, or u is less than or equal to a for t greater than or equal to 0, that means that a minus u is greater than or equal to 0, which is fantastic, because this thing is a minus u. So this whole thing will be greater than or equal to 0, which makes me very happy, because that it should be true, because du by t is a real number. So these are just nice little ways. In physics problems, you can do little checks like this to check you haven't made a mistake. Because if this was negative, or this was less than 0, then you'd be very aware that you've made a mistake, and you can then look through your working and see where you've made a mistake. That's a good little habit in physics problems. Good. So we're all good. Now all we have to do is just deal with this squared. So we can take the square root of both sides. So we get rid of that squared, and now we take everything to the power of a half. And because this is distributive over multiplication, I'm allowed to do this. However, I also have to take the plus minus. So do we take the plus or the minus? Well, remember that u is a variable, and u is always decreasing with time, because as time goes on, these masses get progressively closer and closer together. They never become further apart. So u is always a decreasing function with time. So therefore, the gradient is always negative, which means therefore that du by dt is always less than 0. It's never positive, because these masses never get further apart, because they're under the influence of an attractive force. Now, obviously, I said that du by dt squared is greater than 0, but of course that doesn't mean that du by dt itself has to be greater than 0. In this physical problem, we know that it's actually negative, so we're going to take the negative solution to this. Okay, so fantastic. We've actually got to the stage where we can now separate this equation and integrate it. So bear with me. Okay, so I'm just going to continue doing my work up here. So what I'm going to do is going to bring the dt up here, integrate with respect to time, and then bring this function of u here to this side, and then integrate with respect to u. So I'm going to get integral du a times u over a minus u to the power of a half is equal to minus 2g m1 plus m2 to the power of a half times by dt, integral dt. Okay, now we need to shove the limits in, and the limits, remember, the limits encode the initial conditions. So at t equals 0, u is equal to, well, remember, u of 0 is just a separation at t equals 0, and at t equals 0 they are separated by a distance a. And remember, that was one of our initial conditions that we described earlier. At general time t, u is just general function of t. Okay, so we've separated it. Now we need to integrate it. And to actually integrate this left-hand side, you could use a trigonometric substitution, and you could find the exact antiderivative and then put the limits in, and then solve. So you'd get some function of u on this side, and then you get t on this side. However, the function of u you'd end up with is that you can express it in terms of elementary functions. However, it's just horrible, and you can't invert it in terms of elementary functions. So it's actually kind of pointless to do that, unless you're gagging to find t as a function of u, which isn't that useful. So actually, I'm going to just rearrange this into something nice. I'm going to do some nice little tweaking, and then we'll get something which will actually be quite nice. So just bear with me a sec. What I'm going to do is I'm going to take this a. I'm sure you're all right with me doing this. I'll just drag the a down and just divide it. We both know that that's valid because you just divide top and bottom by a. I'm also going to divide that thing by a. So I'm pretty much removing the dimensions of u, because remember, u is like a physical distance, so you want to divide by a distance. So we know that this u over a is going to validly be just a number, which is just what we want when we're doing sort of integrals and want to gently tweak the mathematics. We love it when the variable we're integrating with is actually a dimensionless number. So again, we got this du here, so we want to divide that by a, which means we need to times it by a as well, and we can times it outside the integral because a is a constant. Okay, now I'm going to make a little substitution. Now you may sort of wonder why I'm doing this, but it will make sense in a minute. So I'm going to make the substitution rho is equal to 1 minus u over a. Now, I would be very impressed if someone actually knew to do this the first time. This is just something I know to do because I spent ages solving this problem the first time. But this is actually the best thing to do at this point, so it just makes sense at this point of the video. Like I said, if you manage to actually do this yourself, then I'm very impressed and I'd love to see your workings. So let's actually put this in. So d rho by du is equal to minus 1 over a. So therefore du over a, i.e. this thing here, is going to be equal to minus d rho. The limits, so now, just forget about the limits for a second. And actually what we can also do is this, we have an a to the half here, so we can put that out there. So we get a to the 3 over 2, and now we can forget about this a in there. What I'd also like to do is actually divide both sides by a to the 3 over 2 as well. And then just define this thing. This is what we often do in physics. Now this thing is just a horrible mess, and but it's a horrible mess, but it's also a constant. So actually, we're going to define this thing to be a constant called kappa. And this will just make the algebra much nicer because I can't be bothered to write that out each time. Plus, these ball pens are quite expensive, so I don't want to be replacing those anytime soon. So, we're now finally ready. Those cancel nicely. So we have integral. When u equals a, rho is 1 minus a over a, which is 1 minus 1, which is 0. So we get rho is equal to 0. At the top, we get when u is equal to u, we get rho is equal to 1 minus u over a. And we have du over a. Remember, du over a is just minus d rho. We have this thing here. Now, u over a, rho is equal to 1 minus u over a. So if we put the u on that side and the rho on that side, we get u over a equals to 1 minus rho. 1 minus u over a is just there. That's rho. All to the power of a half. Oh, I didn't do this. There we go. That's a bit more like it. Thank you to Black Pen, Red Pen. Actually, it was him that taught me that trick. So yeah, just shout out to him. is equal to minus kappa. Remember, we have this kappa, which is defined as follows, and we have the integral of 1, essentially this is integral of 1 dt from t0 to t, so we just get t minus 0, which is just t. Oh, okay, well, this thing looks slightly better, but the limit looks horrible, and it's still something we can't really integrate easily in terms of elementary functions, but that's, well, let's just see what happens next. So, and I just want to remind ourselves of what kappa is. So we get kappa is equal to 2g m1 plus m2 over a cubed to the power of a half. Remember that u is equal to x2 minus x1. This is sort of how these new variables relate to the original problem, and we've got this rho thing here as well. But rho is a dummy variable, so it's just inside the integral. We don't really care about it. Okay, and what do we have here? Well, we have integral. Rho goes from 0 to 1 minus u over a. And, oh, hang on, these minus signs cancel, so I'm just going to cancel these minus signs on both sides. We get d rho. On the bottom, we have rho to the minus a half. So on the bottom, we have rho to the half, so we can write that as rho to the minus a half, multiplied by 1 minus rho to the half. And that is equal to kappa times time. Okay, you might be wondering why I'm fiddling about with this so much, but have a look at this. Let's think about what we've already done in some previous videos. And if you haven't seen them, then it doesn't matter, because you can always revise, or you can just trust me. So let's just remind ourselves of the incomplete beta function. So the incomplete beta function of nm of some variable x is equal to t goes from 0 to x dt of t to the n minus 1 times 1 minus t to the m minus 1. Okay. Oh, it looks. There's just. Let's do something else. Let's rewrite this thing as now minus a half. I mean, why not rewrite it as just a half minus 1? And likewise, a half. Why don't we just write? Why don't we just write it as 3 over 2 minus 1? I'm smelling something. Something smells very strong. I can just smell it coming out now. Now, if we look at this equation, look at this integral, this is just the incomplete beta function. So we've actually got here, we've got the incomplete beta function. Now, in this case, n is just a half, because you've got n minus 1 here, you've got half minus 1 here, so n is just a half. And the m is, well, you've got n minus 1 here, and you've got 3 over 2 minus 1 here, so m is 3 over 2. And what's the argument of the function? Well, you've got 1 minus u over a up there, and you've got x here. So the argument of the function is just 1 minus u over a. That's, wow. That is, if you're confused with this, please look at a previous video. But I find this very exciting because with the mathematical machinery, which are beta functions, we can now actually express u as a function of time. So we now have this relationship, which is that the incomplete beta function of 1 minus u over a, where u is a function of time given by this, and kappa is given by this, is equal to kappa times t. Now, we want to solve for u over a. And unfortunately, though, it's inside the argument of the function. So what do we do? Well, if we want to unpack a function, if we want to sort of take the arguments out of it, then we need to just, well, let's just take the inverse of both sides and see what happens. So, inverse incomplete beta function, 3 over 2 of both sides. And, well, the inverse function of any function itself just cancels it, and you end up with the argument itself. Now, I know that I defined the inverse incomplete beta function the other way around, but this is also true. The inverse of the function itself, the inverse of the function of the argument will just give the argument itself. So the inverse function cancels with the function, and you end up with 1 minus u over a is equal to the inverse incomplete beta function of kappa times time. So after all that, all those integrations and changes of variables, we finally arrive at our solution. So we have 1 minus u over a is equal to the inverse incomplete beta function, a half to 3 over 2 of kappa times 2, where kappa is given by this and u is given by this. We can now evaluate u. We can now rearrange this thing for u. So we now have u of t is equal to a times 1 minus inverse incomplete beta function half 3 over 2 of kappa times t, where kappa is this constant here. Okay, so we can now, we've actually finished all the integration and equation solving. We can now plug in our original u back in again. And we now have a relationship between x2 and x1. Now, is this problem solved? Well, we want to get x2 and x1 explicitly. I mean, we've got x1 and x2 in these formulae. Is this really a solution? Well, unfortunately, we haven't solved the problem yet, because we've only got a relationship between x1 and x2. We don't have, and what we want is x1 and x2 as explicit functions of time. So we actually need to do some more work, unfortunately. So where are we going to get any more solutions from? Well, we need to look up at our equations again and try and find some more kind of symmetry within them. So let's just take this solution as done. We're very happy with it. Let's try and find something else from these formulae. So now, if you stare at these long enough, you can see that the right-hand sides of these formulae actually look pretty similar. I mean, you've got a gm2 on there and a gm1 there and a minus sign, but the function relationships are actually the same. You've got a 1 over x2 minus x1 squared. So, okay, so what is the relationship between 1 and 2? Well, you see you've got an m2 there. So if you multiply this equation by m1, you'd actually get this thing. And if you multiply this equation by m2, you'd actually get this thing after you multiply it by m1. So how about we take m1 times 1 and add it to m2 times equation 2. Seems legit. Let's see what we end up with anyway. So on the left-hand side, we get m1 times x1 double dot plus m2 x2 double dot. And on the right-hand side, we get g m2 m1 divided by x2 minus x1 squared. Add, in this case, minus g m1 m2, because we're multiplying it by m2, over x2 minus x1 squared. And, oh look, since m2 and m1 are real numbers, they commute, so these two actually cancel out. And we're left with this thing being 0. Okay, so we get this relationship between x1 and x2, and actually this is just a statement of Newton's third law, which is that the force of 1 acting on 2 is equal to minus the force of 2 acting on 1. In this case, you just put that onto that side and it's added and equal to 0. So actually we could have got this relationship very early on in the derivation. We could have actually got it straight away just by looking at the forces. So that's very nice. It means we have found another symmetry now. Okay, so what's there left to do? Well, just like last time, we just need to integrate these equations. So let's integrate it once. Basically, we're integrating term by term, which is possible because the integral operator is linear, and knowing that that the antiderivative of 0 is a constant. However, if you're not fully convinced, then if you can go from this equation to this equation if you just take the derivative of both sides, because the derivative of this a, which is constant, is just 0, and this side will just give you, well, the derivative will only actually act on these x's because the m's are constant. So you get these x1 and x2 double dotted. So you basically get this thing again equaling 0. So without loss of generality, because we put this general constant here, then this equation implies this equation is true. Great, so we've integrated it once. So we need to find the constant of integration. So now, how do we find the constant of integration? We need to use our initial conditions. So let's just evaluate both sides of the equation at t equals 0. So at t equals 0, we have x1 dot of 0, which is 0. So we get m1 times 0 plus m2 times x2 dot when t equals 0. x2 dot when t equals 0 is 0. So we get m2 times 0 is equal to a. And 0 times anything is 0, so we get a equal to 0 plus 0. So a is just equal to 0. And so we can now replace this a with 0. And, well, let's go ahead and integrate it again. So by the same logic, we find that m1 x1 plus m2 x2 is equal to some other constant b. Now, I forgot to mention that this statement here is just a statement saying that momentum is conserved in the centre of mass frame, because considering neither of the masses have any initial velocity means that we're actually in the centre of mass frame, because the centre of mass isn't moving, and in the centre of mass frame the total momentum is added to 0. So you could have got that result physically, but there you go. So we now need to plug the initial conditions into this. So at t equals 0, we get m1 times x1 when t is 0. Now x1 at 0 is just 0, so that's just 0. And m2 times x2 at t equals 0, x2 at t equals 0 is a. So we get m2 times a is equal to b. And because that term doesn't contribute, we can just therefore conclude that b is equal to m2 times a. Okay. So this was much easier. So we've now got another relationship between x1 and x2. So by some nasty integration, we've gotten this relationship between x1 and x2, and through some much easier integration, we've got this relationship between x1 and x2, and, well, we now have two linear simultaneous equations in x2 and x1. So now we are actually able to solve for x2 and x1 as functions of time, which is what we were looking for. So next video, we are going to be solving this system of equations for x1 and x2. We've got the nuts and bolts, we've got the meat and potatoes out of these equations now. Now we can just look at these, because we've now solved these equations, got the relationships between x2 and x1 that we want, and we've used the initial conditions and got these solutions. So please join me for my next video, when I will find x1 and x2 explicitly and get some nice and interesting results. Thank you for watching.